Now that we're getting into molecules and kinetic molecular theory, it's important that we can quantify the number of molecules that are in a given amount of the substance. To do that by counting molecules and actually delivering a number of molecules or atoms would be an outrageously large number. So instead, we report that in terms of the number of groups of molecules, and we group them in large groups called the mole. In this video, we'll talk about what the mole is and how it's used in physics and chemistry to talk about these large numbers of molecules and convert those numbers of molecules into a mass of the substance. I want to start out by just referring to the fact that we use words to describe groups of something a lot in our everyday language. A pair of shoes, we know, would describe 2 shoes. A dozen roses, we know, would describe 12 roses. If I said I had 5 dozen roses, we know that it has a meaning associated with it beyond just the number 5. 5 dozen roses doesn't mean 5 roses. It means 5 times 12 or 60 roses total. It's just an easier way to talk about those numbers that end up getting larger. They're grouped into these amounts that are commonly seen together. We see other examples of this as well that are a little bit more confusing. A baker's dozen we know is 13. A score is 20, like Abraham Lincoln said 4 years ago is 87 years. It's just a fancy way of saying that. And a gross is a dozen or 144. We are not going to be using these to describe molecules because even a gross is a tiny number of molecules and something that we wouldn't be able to measure in any realistic way using instrumentation that we have. So what we're going to do instead is we're going to use another grouping called the mole. So whereas a gross had 144, one mole has 6.02 times 10 to the 23rd, or 602 sextillion atoms or molecules in this substance. And reality is you wouldn't have to have atoms or molecules. You could describe anything using a mole. You could say I have a mole of golf balls in the same way. It's just a huge number that you would never have that many of any physical quantity like that. This is also known as Avogadro's number, named after the scientist Amadeus Avogadro. And because of that, sometimes this number is given the shorthand of N sub A for Avogadro's number. And he's a fine looking man. So to quantify and conceptualize just how large this number is, I think there are a couple of useful ways that we can think about it, because atoms being so tiny means that this many atoms is a reasonable number of atoms. But if we had that many golf balls or something else, it would be a huge number. Just to see what this looks like, not in scientific notation, you've got a lot of zeros following that 6.02 or 602. So just to give you a couple other examples of what this looks like, I want to play a short clip from a TED Ed that does a really nice job with this.
Yep, this number has a second name. The mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank.
So I think those examples, especially that money one at the end, do an amazing job of showing you just how huge this number is. But if we talk about atoms, it's a reasonable amount of a substance. So let's look at what that actually means in terms of some elements that we are familiar with. First of all, if you're interested in more of these kind of what ifs about mole and how large that is, I recommend a blog called What If. It's also a book by Randall Munroe, and one of his chapters in one of the blog posts is about what would happen if you gathered a mole of moles, the furry creature, And it's phenomenal. So in chemistry and in atomic physics, when we get into that, atoms don't weigh very much on their own. One carbon atom is 1.9927 times 10 to the negative 23 grams. Or, not in scientific notation, all of these zeros before you start getting numbers. That is not a number that we're going to measure individually on a balance. But if you were to gather a mole of carbon atoms and multiply that by 6.02 times 10 to the 23rd, you would get approximately 12 grams. That's the same amount that is shown here on this balance. And that 12 grams should be familiar if you ever looked at a periodic table. On carbon, the average atomic mass of carbon is 12.01. So that is going to be also known as our molar mass. That's how many grams if you gather a mole of a substance. So we can use that to define what a mole is. It's actually based on this idea of carbon. So this is an IB question that's happened in the past. You should be able to define what a mole is. Is it A, 1/12 of the mass of an atom of the carbon isotope carbon-12? B, is it the amount of a substance that contains as many elementary entities as the number of atoms in 12 grams of the isotope carbon-12? Is it C, the mass of one atom of the isotope carbon-12? Or is it D, the amount of a substance that contains as many nuclei as the number of nuclei in 12 grams of the isotope carbon-12? Now, all of these are kind of dancing around the same idea, but a key feature here is this idea of elementary entities, that this could talk about atoms, it could talk about compounds, it could talk about molecules, it could talk about basketballs or moles of moles. The best answer here is B, that it is associated with the number of atoms in carbon-12, 12 grams of carbon-12, but it could be the amount of any substance that has that number of atoms or molecules. So this molar mass is the mass of 1 mole of a substance. We're going to measure that in grams per mole. And if you see it on the periodic table, that average atomic mass can be used as your molar mass. So molar mass of nitrogen is 12.01 grams per mole. Sulfur is 32.07 grams per mole. You just read it right off the periodic table. It'll be given to you, not something that you need to have memorized or know off the top of your head. If you had a stack of pennies that looks like this, and if they were all pure copper, so it have to be pretty old pennies, we can figure out how many atoms there are in that stack if we knew that it was 1 mole of copper. The number of atoms is Avogadro's number, 6.02 times 10 to the 23rd. I could rephrase that question and say, all right, what is the mass of that 1 mole of copper? If we have a periodic table, we can find the molar mass. That is 63.55 grams. You can also use those two answers to answer this last question. What is the mass of 1 atom of copper? Well, if 1 mole is 63.55 grams and there are 6.02 times 10 to the 23rd atoms in a mole, you just divide it by Avogadro's number. You should end up with a really tiny number because it's the mass of 1 singular atom, and that is about 1.05 times 10 to the negative 22nd grams. So really tiny. You'll see that is heavier than what a carbon atom was, because copper is a heavier atom, more electrons, more protons, more neutrons inside it. If you have more than 1 mole, it's a pretty easy conversion. So 3 moles of copper, you just multiply your molar mass by 3 to get your 190.65 grams. If you have 28 grams of nitrogen, looking at your periodic table, seeing that it's 14.01 grams for every mole, you can figure out how many moles of nitrogen there are. Of course, 28 is about 2 times that, so it's about 2 moles of nitrogen that show up in 28 grams of nitrogen. IB likes to ask this in a variety of different ways, and usually it's a little bit more complicated. So if I were to ask you, what is the mass of carbon-12 that contains the same number of atoms as 14 grams of silicon-28? You can figure out how much carbon-12 there is if you know how many atoms there are, or roughly how many moles of silicon-28 there are. Well, 14 grams of silicon-28, this 28 represents the mass number of silicon. So I've got 14 grams and is 28 grams for a mole, which means I have half a mole of silicon. Now, half a mole of carbon, we know that carbon-12 has a mass of 12. So half of 12 grams is 6 grams of carbon. So a lot of the questions around this are going to be kind of these two-step questions that you look at one substance and then compare it to another substance. A sample of 4 grams of helium and 20 grams of neon. A sample contains 4 grams of helium and 20 grams of neon. The mass number of helium is 4. The mass number of neon is 20. What is the ratio of the number of atoms of neon to the number of atoms of helium? Well, we can look at these individually. Helium here has a mass number of 4, and we said that there were 4 grams, which means that 4 grams and 4 grams per mole, we just have 1 mole of helium. We can do the same thing for neon, 20 grams of neon, and the mass number is 20, means that I got 20 grams for every 20 grams per mole. We got 1 mole of neon as well. That means that the ratio of neon to helium is 1 mole per 1 mole. That's just 1. So it's a pretty boring question there. But each of them was 1 mole, so the ratio is 1. Finally, you should be comfortable doing this for more than 1 atom. So if you have a full compound, like magnesium nitrate here, there are several atoms that are part of that compound. You can see here that there's a magnesium surrounded by 2 nitrates is how that will form a compound. We're not going to worry about that in this class. That's a chemistry topic. But you should be able to identify from this formula how many of each atom is going to be present. So there's 1 magnesium, and these parentheses distribute. So there's 2 nitrogens, you'll see that there, and 3 times 2 oxygens. You'll see 6 oxygens there. So if you are given these parts of the periodic table to find the molar mass of each of these individual atoms, to find the total molar mass, you're just going to add them up. So you got 1 magnesium at 24.31, you've got 2 nitrogens at 14.01, and you've got 6 oxygens at 16.00. You add them all together, and you should end up with about 148.33 grams for every mole of magnesium nitrate. All right, a fairly short video, fairly short topic. You should be able to describe the importance of having a large quantity like the mole being defined. So why would we need that? Well, it's because the molecules and atoms that we're talking about are so tiny. So that's how much we need in order to be a measurable quantity that we can actually look at and quantify in that way. You can also use the average atomic mass of an element or compound to convert between mass and moles and number of atoms. So any of those conversions or comparisons that we saw in the questions in this video.